Derivation of energy operator. Introduction. Operators are meaningless on their own unless applied to something. Back to school. Basic operators are sum, difference, product, quotient. Sum is what we call plus, addition. Difference is minus, take away. Product is times. And quotient is division. 7 plus 3 equals 10. The plus on its own has no meaning. It's meaningless. But when you apply it to 7 plus 3, you get 10. 7 and 3 are operand, plus is the operator. In quantum mechanics, operators are only meaningful when applied to a function. Operators in quantum mechanics have to wear a hat so that they can be recognized as an operator. Here are some examples of quantum operators. This is position operator, and it's applied as x. This is time operator, momentum operator. We've derived that before. And this is velocity operator. So that could be that or that. This is kinetic energy operator. H hat is Hamiltonian operator. And then you've got angular momentum. Energy momentum is what we're deriving today. So it could be that or that. So derivation of psi equation. Psi, or wave function equation. Psi is a wave function. And psi is written as psi is psi, and it is a wave function for a particle behaving as a wave. X is the space coordinate and t is time. A is a constant. To modify I theta into wave equation. I is what we called iota, a Greek letter, and that equals root minus 1, which is a complex number. If you have a complex number, a plus ib, I is the imaginary, and that equals to I equals to root minus 1, equals to root minus 1. E is Euler's number, or a mathematical constant approximately equal to 2.71828. So this is the function that we will describe the equation of a wave matter of a particle. But we need to talk more about the E value. I theta is equal to cos theta plus I sine theta, and this equation is called Euler equation. So what we're trying to do is use this equation to derive a function equation for wave particle behavior. We have psi in space, so this one is in space, and this is time. But we also have another variable, which is the angular displacement. So what we're trying to do is change the format of angular displacement into space and time. So we want to replace the angular displacement into space and time parameter. So that is, we want to take angular displacement and we want to turn it into a function of x and t. So back in school, we know what linear displacement is. Linear displacement is basically distance with direction. And we also know linear velocity, which can be written as v or c, and that is speed with direction. And we can write the equation for v or c to be equal to x over t. And this is what we called linear velocity equals linear displacement over time. Bear in mind that can also be c or v. But what about a particle moving at an angle? So if you have a particle, start at A and then move all the way to B, it will generate an angle, which is what we call theta. And therefore, it will have, since it's got a displacement, angular displacement, it will also have angular velocity. So the angular velocity, which is what we called omega, omega is angular velocity. Angular velocity will be equal to angular displacement over time. Just like you have linear displacement over time, to give a linear velocity, you have angular velocity equals angular displacement over time. So we can rearrange and make angular displacement equals angular velocity times time. So we have the equation psi x t, which equals a e I angular displacement, and that would transform itself into psi x t equals to a e I omega t. So omega t can now be in two forms. The first one being that omega t can be written as 2 pi f t. Why? Because 2 pi f is omega. And in 1900, Max Planck, so 1900, Max Planck and Albert Einstein in 1905 proposed that E equals HF. So now we can make F the subject So F equals E over H. Therefore, if I take the F now as E over H and put it back into that equation there, we now get a new omega t to be equal to 2 pi E t over H. We also know that omega t equals to 2 pi ft. But we know in basic physics that C is equal to F lambda. Therefore, F is C over lambda. So if I take that and put it into there, we will get the omega t equals to 2 pi C over lambda t. But at the same time, we know what C is. C is basically equals to x over t. And so if I take that and put it into there, we will then get omega t equals 2 pi x t over lambda t. As you can see, the t here, we cancel that t. And so omega t will be equal to 2 pi x over lambda. So we know that omega t equals 2 pi x over lambda, since we've cancelled out the t's. Therefore, let 2 pi over lambda equals k. We might then write omega t equals kx. If we then take the omega t to the right, we might get kx minus omega t will be equal to angular displacement. Because angular displacement can be 0 or can be a variant of 0, depends on x. So that will be the angular displacement. So from the general equations that we had before, where psi x t is equal to a e I angular displacement, so we can replace the angular displacement by taking that and put it into there. So therefore, we get psi x t will be equal to a e I open bracket kx minus omega t. And this is a very famous equation that a lot of people tend to write out as the beginning for the derivation of the momentum operator or energy operator. As you can see, we've managed to convert the angular displacement into a function of x, which is x here, and time, which is time over there. So now we need to convert this one more time by working on these functions here. So what we're going to do is apply the function of Einstein and Max Planck and also Louis de Broglie. So we already proved that omega t equals to 2 pi e t over h. That is when we talked about Einstein and Max Planck, where E equals hf. The next thing we need to talk about is Louis de Broglie. So Louis de Broglie talk about wave equation in 1924, where it said lambda is equal to h over p. So that's Louis de Broglie. Introducing Louis de Broglie in 1924, we can now apply that to the other equation here. So we're going to use this one for that equation over there, and we're going to use this one with Louis de Broglie. So Louis de Broglie then said, if you have k equals 2 pi over lambda, and we know that lambda is h over p, so now we can replace that with 2 pi over h over p. So what I've done is I've transferred that into there, and that then become 2 pi over h times 1 over 1 over p. 1 over 1 over p is p, and that becomes 2 pi over h p. 2 pi p over h. So now we've got k to be 2 pi p over h, which we're going to put in here. And we're going to change the omega t into there. So now let's go to the next part of the equation. So we started off with this equation, and we're trying to change that angular displacement to have a component of x and t. And we did that by arriving with this wt, omega t. And from then, we then managed to change that into kx minus omega t, and that now k and omega t is being replaced with k and omega is being replaced with the 2 pi over hp and minus 2 pi e over h and 2 pi e over h. So what that is now, first of all, let's talk about what we've used in this equation. So we have used lambda. So lambda is lambda, which is basically wave length. So if you have a wave like that, and the length of a wave from the beginning to the point when it starts to repeat itself is lambda. And we've used h, which is what we called Planck constant, and that has a value 6.626 times 10 to the power minus 34 joules second. We also use P, and P is what we call momentum, and that is mass times velocity. We've used E, and that is energy. So, but from here, what we now have is a very different form of equation. And so let's talk about this. As you can see, there's a common factor here, 2 pi over h. So that's what I'm going to do. I'm going to take the common factor out. So we have psi x t equals to a constant e I 2 pi over h into bracket px minus et. So what we got here is px minus et. According to one Heisenberg, who states that the position times the momentum will be greater or equal to h bar over 2. Or you might say the time times the energy will be greater than or equal to h bar over 2. As you can see here, this is E times T. E times T here has a unit of H. So here too, P times X, P times X has a unit of H. So what is the unit of H? Unit of H is joules seconds. So H has a unit which is joules seconds. And that meant here joules seconds, so that's good. So, but what is h bar? Well, h bar is reduced Planck constant, which is h over 2 pi. So that's called reduced Planck constant. So if I have h bar equals h over 2 pi, 1 over h bar will be equal to 2 pi over h. And that is what I've got here. Common factor here is 2 pi over h. So I can replace 2 pi over h with 1 over h bar. So now I can write the new equation as psi xt be equal to a constant E I over h bar, open bracket, px minus et. So this is the new format that we need to put this equation into. So what I'm going to do is just draw the arrow there. So that was the journey that we need to take to get to the point where we need to now use this equation. We now need, this is the equation we need now to differentiate. If you want to find the momentum, we differentiate with respect to x. And if you want to find the energy operator, we differentiate with respect to t. So now this is the new equation that we need. If we want to differentiate with respect to x, we're able to find the momentum operator. And if we differentiate with respect to t, we find the energy operator. So now if we differentiate with respect to x, here we get the momentum operator. And if we differentiate with respect to t, we get the energy operator. If you're to differentiate an exponential function, because we've got exponential function here, if you're to differentiate an exponential function, you will get the exponential function back times the derivative of the exponent function. And the exponent function is nx. If you differentiate nx, you get n back. And therefore, but the the function itself that you got back is y. So therefore that would be yn. So the y dx is going to be the function itself times the derivative of the exponent function. And we've got that here. Psi is the function itself. And the derivative of this we're going to get back. So we get this back. And if we're differentiating with respect to x, so we have to differentiate this one. That's the function of the exponent. And that's because t will be constant. So that will be 0. And then if we differentiate px, we get p. Or if we differentiating with respect to t, then this will be a constant. If we differentiate that as 0, and if we differentiate et with respect to t, we get e. Also, if we are to differentiate with respect to x, but we've got two variables here, x and t, it means we have to keep t constant. Because we're differentiating and keeping one constant, we're going to use something called partial derivative. And partial derivative is written as delta over delta something. So we're going to write this as partial derivative of, with respect to x, of the psi function, which now will be equal to we're going to get a whole function back, which is the a e I over h bar, open bracket px minus e t, and then we're going to times that, what you get back, by the derivative of this one here. So if we differentiate et with respect to x, we get 0. If we differentiate px, we get p. So p times I over h bar. So that would be I over h bar p. At the same time, if we differentiate with respect to t, and that would be partial derivative of wave function over the t, and that will be equal to, again you get the same function back, e I over h bar, open bracket px minus et, times the derivative of et with respect to t, and that will be e, and if you differentiate in px, that will be 0, and so that will be minus e. If you differentiate et, you get e, and then that is e, that's minus e times I over h bar. So what we're going to get is basically times minus I over h bar e. So if we carry on with this one, we're going to get, but we know what the function is here. That is the function here. That one is the function which we started with, which is psi. So that's psi times that. So we will get back partial derivative with respect to t equals to psi minus psi, because there's a minus there, I e over h bar. Likewise, if you do the same thing here, you're going to get partial derivative of psi over with respect to x. Again, that's psi there, so that's psi I p over h bar. Now, the psi here we cancel with that one. Likewise, psi here we cancel with that one. So what we're going to get now is here you're going to get psi over dt, partial derivative, we go to minus I over h bar e. Likewise, for here, you're going to get psi over dx equals to I over h bar p. So far, this is what we've got. Now, what we can do now is to make p the subject here and make e the subject there. And so here, if we make p the subject, we get P equals to h bar over I partial derivative with respect to x, and on this side here you get E, making it subject, minus h bar over I partial derivative with respect to t. So far, these are the operators in the direction of x. So it has subscript x, and this is the operator here. So now it'll be energy operator. So now this is the momentum operator, and that's the energy operator. One thing to watch out for is if we have 1 over I, we need to rationalize the denominator. So we have a complex, which is I, and then we have to use something called a conjugate complex. Conjugate complex. The conjugate complex of I is minus I. And if you have minus I as a complex, the conjugate will be I. So to rationalize 1 over I will be to multiply both numerator and denominator by its conjugate complex. So that will be 1 times minus I over I times minus I. And the minus we cancel out. So we get I over I squared. But let's talk about I squared. I squared is minus 1 root to power 2. And that could be minus 1 to power a half, all to power 2. And that is minus 1 to power 2 over 2, which is minus 1. So I squared is minus 1. So if we put that here now, we're going to get minus I. So 1 over I is minus I. If 1 over I is minus I, so let's just put it there, minus I, therefore 1 over minus I is going to be I. So you can see we can now write this momentum operator in a different way. So for Px operator, that would be, well, 1 over I is minus I. So that would be minus I h bar partial derivative with x. And for the energy operator, so let's just write the energy operator. So that would be E operator will be equal to, well, we got 1 over minus I. So 1 over minus I is I. So that would just be I h bar partial derivative with respect to t. So the new operators that we are looking for, the energy operator. So that's the one we were deriving today. But I just added the bonus of momentum operator for you, which has been done previously before. And that momentum operator again, another way you can write it, and energy operator, another way you can write it.